This lesson is about perpendicular bisectors. We've already learned how to construct the midpoint of a segment. Let's review that. Start with a line segment. To construct a perpendicular bisector, we'll take our compass and set it somewhere between a half and a whole. Scribe an arc. Leave it set at the same distance, go to the other end point of our segment, and scribe another one. Previously, what we've done to find the midpoint is to line up the straight edge with the intersection of the arcs and make a mark, that being the midpoint. Now we're going to draw a line through, and we're going to observe that this both bisects the line segment and is perpendicular. We've previously established that it makes two congruent segments, therefore bisecting it. Now let's look at how we know that it's perpendicular. Come from the intersection of the arcs at the line, and let's draw a segment to the end point of our original line segment. Oops. See what we can do with that. These two segments, the orange one and the brown one, are congruent. Why are they congruent? Well, we drew them as radii of congruent circles. In other words, we didn't change the setting on the compass when we did it. So these all are congruent. The common side is congruent in both triangles, so this is side, side, side. These triangles are congruent. The two angles here, where the purported perpendicular bisector meets the original line segment, are corresponding parts of congruent triangles, so they are congruent. So we have a linear pair that is congruent, which according to a previous theorem tells us that this is a perpendicular line. So this is a perpendicular bisector. Let's look what happens if we try different sizes of arcs. I'm going to make it a little bit bigger. Oh, look, when I do that, it's on the same perpendicular bisector. Assuming I'm a pretty good drafts person here, I'll extend it some. What if I make one that's even bigger? Will that still work? Who knows? Let's try. Yes, it does. What we're seeing here is a variety of triangles from the endpoints, which are all congruent left to right, the same way that the top two were. In every event, this point is going to be on the perpendicular perpendicular bisector of the segment. What we see, therefore, is that any point on the perpendicular bisector of a segment is equidistant from the endpoints, the perpendicular bisector theorem. And the converse, which we just saw as well, which is that any point that is equidistant from the endpoints lies on the perpendicular bisector. Okay, so what possible use is this? Well, more use than you would know. I look out the window here, and I just tried to take a picture, and I did, but it won't download, so I can't get it to you. Imagine yourself looking out the classroom, the window of the classroom, and there's apartments across the hall. And rising behind the apartments is a cell tower antenna that looks kind of like this. It's very long and skinny. It's got red and white sections in it. It's held up by guy wires. So let's think. It's this long, skinny antenna with a cell antenna on top of it. This long, skinny structure with antenna on top of it. I wonder how they got it up there. Well, let's think. It would need to be perpendicular. The reason it would need to be perpendicular is if it's not, it's probably going to fall down. Gravity's going to pull on it, and it's going to fall down. If it's perpendicular, then gravity is much less likely to have that effect on it. So somebody who wants to put it up wants it to be perpendicular because they want gravity to work with them and not against them. So how are you going to get it to be perpendicular? Well, you got this long skinny thing. It's laying on the ground. You want it to be and you want it to be perpendicular. So I guess you could shimmy up the pole with it not connected to the ground very good and just try to figure out if it was perpendicular. That's not my choice. That's not a particularly good recommendation. So what you could do is lay the pole out on the ground and use the perpendicular bisector theorem Converse, which would say that if these are congruent, the guy wires, the distance from the endpoints to the point on the perpendicular bisector, if they are congruent, and also if the are congruent distances from the anchors on the ground, the endpoints of the segment, to the base of the antenna, that the antenna will be perpendicular. So again, you can measure this on the ground really easy. All you do is measure it off. So you have an antenna where you want it to be, maybe attach it there. 2 anchors to hold the guy wires. Make sure the anchors are equidistant. Measure the length of the wire going up to the top. Make sure it's the same. Attach it, and then put a hook on it, pull it all the way up, and stand it up. It will be perpendicular. Therefore, it's going to stay up. One thing I know, I'm pretty sure the one across the street here, down the ways that I can see, is perpendicular because it didn't fall down in Hurricane Harvey, and it didn't fall down in the hurricane before that, and it didn't fall down in the hurricane that never happened, that we all evacuated the town and there was no hurricane. It didn't fall down. It's been there. I'm pretty sure it's perpendicular. Next time you drive by on Glenmont, look at how it is, how there are guy wires on it. Notice that there are guy wires at different levels. That holds it rigid. It's a pretty skinny antenna. It's going to whip in the wind if you don't have some support for it, and these wires will provide that support. And they're at an appropriate place to keep it from whipping in the wind, that the engineers have figured out where it should be, and when you're an engineer, you can do the same thing. I'm thinking, some of these principles of geometry have been around for thousands of years, a couple of millennia plus. Some Greeks and some other folks laid around and, tended the sheep or whatever and thought about this kind of stuff. I'm thinking that when those people and people since then have thought about geometry and figured out all this stuff, that what they had in mind was that in 2,000 years there would be somebody that would need a pole to put their cell antenna on. I'm thinking that's exactly why they did it. They said, in 2,000 years somebody's going to want an antenna with a cell thing on top of it. No, they did not. They did it because it was interesting, because they were figuring out how the world really works and quantifying it, writing it down, analyzing it, and learning it so that they could learn more. So what does that mean about you? If you'll learn your geometry and your other subjects, but mainly your geometry, and learn it really well, do your proofs, learn the concepts, learn the reasons, then you'll understand it well enough so that in a decade or two from now, when it's time for someone to innovate something new that we haven't even thought of yet, you'll be the one that's poised to do that. If all you learn about geometry is how to check, circle in, bubble in A or B or C or D, you are not going to be that person. You'll be the person whose job goes away because that skill is no longer needed. I want all of y'all to be people who think, who reason, who are going to be on the cutting edge and have the capacity to be the next new thing. So that's what this is about. Okay, back to this. Another application of the perpendicular bisector theorem. We have here, this is a picture of the Fred Hartman Bridge. Over the Houston Ship Channel between Baytown and LaPorte. Baytown's over here, LaPorte's over here. The ships pass through the Houston Ship Channel through here. Behind it is the various industry that's on the Houston Ship Channel. Notice that this is an application of the perpendicular bisector theorem and its converse. This is a cable-stayed bridge. It's not a suspension bridge. Here's a diagram that shows kind of what it looks like. A cable-stayed bridge. In it we have a cable. It's a big old cable wound together of wire. Go over the bridge sometime. Look at it. It's wide. It's like big. Okay. One cable attaches to a section of the bridge here, goes up to a tower, which is a perpendicular bisector, and down to the other side and attaches to a section of bridge that you drive on the other side. Each one of these attach across it. Each one of the guy wires, the very huge guy wires that hold it up, the cables that hold it up, are congruent on either side. Now up here, they can shift a little bit and they hold each other stable by doing this. This is where you drive. This is the perpendicular bisector of all the cables. So learn it, and you too can be an engineer and innovate. Wouldn't that be great? Here's a couple of examples of how this will work. Perpendicular bisector theorem converse. Notice if you have that it's perpendicular and that they're equal, therefore it's a bisector. That means that the guy wires are the distance from the end point to the perpendicular bisector are congruent. So to solve this, you can say 5x equals 4x plus 3, and that's just first month of algebra, you can solve that one. Here's another example of the same thing. Laying sideways, doesn't really look different, isn't really different. It is a bisector because the distance between the two endpoints, from the endpoints to the bisector is the same, and it's perpendicular, it's marked that way. Therefore, 3x minus 6 equals x plus 18. First month of algebra will solve that for you. Here endeth the lesson.